Okay, wonderful. So yeah, so I'm Nina, you know that now. So at Ospin, we are automating and digitizing bioprocesses in different fields, mainly, as I've already been said, in tissue engineering, cell therapy, and obviously culture meat. So today I'm gonna talk about control systems for bioreactor. And the first part of the presentation is gonna be a bit kind of normal in the sense that I will show a few slides where I'm gonna talk about how a control system for culture meat should, in my opinion, look like. And the second part is gonna be more interactive and I hope also a bit more fun in the sense that I'm gonna show you our control system and we are gonna program up bioprocess together and you will also be able to give me feedback and program something with me. So in culture meat, we are trying to establish a bioprocess, obviously, and usually from a high level point of view can be described like this. First, you need to isolate your cells, then you need to expand your cells, and then you need to differentiate and mature that usually in fat cells or muscle cells. Now, obviously, we want to automate such a bioprocess for many different reasons, because we want to reduce costs, because we want to increase reproducibility. And for that, we need bioreactors. And in the field, there is a discussion which bioreactor type is best. It depends a bit on the cell line you have, the bioprocess you have. It might be better a certain type of bioreactor or another one. As Ospin, we are also in this discussion because at the end we are also bioreactor manufacturers. But today I'm not really going to talk much about the bioreactor, but more about the control system for the bioreactor. And before I enter too much into details, I would like to give a definition of control system because so that we are all on the same page basically. And a control system is a system that translates your bioprocess steps. So what are you doing with your cells into instructions for your bioreactor, which then as a job he has to carry out the steps automatically, obviously. And we believe that we can help reducing R&D, but also production costs by having a control system having specific requirements or features, depending on how you want to call it. And the idea is that now I'm gonna go through this requirements of feature together with you now, and then I'm gonna show you why I do believe that this feature allow us to reduce the cost of R&D in the R&D phase and in production. So maybe one of the first features you need to have is that your control system has to allow a receipt-based approach. What's that mean? Very often devices out there, you can only say, I want the temperature to be 37 degrees and I want my pH to be 7.2. And that's it. And then if you want the temperature to be 35 degrees, well, you need to start a new process. You need to reprogram the machine, basically, or tell the machine again what to do. We believe that it's very important that you can program all your steps before and then let the machine do all of them. Like you want to say, for 2 hours, you should be at 37 degrees and pH, say 7.2. And then after these 2 hours, the bioreactor should go at, say, 36.8 and the pH should be, I don't know what. So, and so on. And you need to be able to program virtually an infinite number of phases and then let the bioreactor do all the rest. And also, I believe that it is very important that we can program complex bioprocesses. So not only like step by step, but also that we can have stuff like, if my temperature is between 36.9 and 37.1 for at least, say, 10 minutes, then jump to the next phase of my bioprocess. Or let's assume I have, I don't know, 3-4 phases, and I say, okay, this phase A, B, C, these 3 steps, I want them to repeat now 20 times. This also should be easily possible. And all this without being an engineer or having studied computer science. It should be super intuitive and it should be like immediately obvious how to do that. Also, I really believe that it's important to use modern technology and to have all data digitized which means it's very important that I can program my bioreactor basically from my computer, from my laptop. In principle, I should also be able to do that from home. And it's very important that all my data, all my process instruction, all the stuff that my bioreactor is going to do, is performing, must be saved all in the same place. And I always know if I go there, I find all information regarding my bioprocess there. And the easiest way to realize that is through a cloud application. It's also very important that the control system is in principle able to integrate different devices, because especially in the R&D phase, you usually are not working with only one device. You're maybe trying out different bioreactor types, or we are combining one bioreactor with another device because you need these two devices to work together. So it's in principle very important that from one same interface, you can control different devices. Why? Because then all the data, all the instruction, everything is again centralized, and you don't have this nightmare anymore that some data are stored in one device. You need to take them out with a USB stick or somehow get them and put them together with the data from another device. Everything should be just centralized in one place. Also, you want to make sure that if you start now working with a control system, then if you start to scale up your process, it's not that then suddenly, oh, I have to change completely my control system because it doesn't support this other device, or this device that now is bigger. You want to be able to have a control system that controls any device size. And the same applies for the number of devices. It's not that if at some point we're in a pilot plant phase and now suddenly you need to have 100 devices or 1,000, and then suddenly your control system doesn't support that. You want a control system that supports any number of devices. You have one interface, you see all devices there, you can just apply, for instance, the same process to all of them in parallel. And the last point is that you want to be able to add to your process data all other data that cannot be automatically recorded. Like all the steps that the bioreactor is running are automatically recorded, obviously, with such a control system. But let's assume you make some observation yourself. You as a technician, you observe certain things, and you want to be able to enter this information and to have this information coupled to the data that the device is producing. So it's what is called an electronic lab book. And you would like this to be integrated in your control system so that, again, all data are in one place. And I was promising at the beginning that I would have explained to you why I believe that this feature can basically reduce the costs that we have in the culture-made field. The first obvious point is that if I have everything automated and digitized, I have higher reproducibility, I need less manpower. This is kind of trivial, and it applies to any system out there that goes in the direction of automation and digitization, obviously. But for instance, a receipt-based approach really allows you to really optimize your bioprocess, because you really have done a system that can help you explore your bioprocess and develop the optimal bioprocess. And think about, especially in cultural meat, where we need to reduce costs. To reduce costs, we need to have optimal bioprocesses. So you need a control system that allows you to do that. Also, the fact that if you have a system that allows you to have all the data in one place, you are not losing time in putting data together or in programming machines separately. This is also very important. And also, like, by not losing time, you're also not losing money, right? An integration of a lab book, it will allow you later. Now, the field starts to talk about regulation. And I can tell you from other fields, we are in the field in cell therapy, for instance, where there are very strict regulations in terms of good manufacturing practice, for instance. And it's a lot about documenting, and again, documenting. And if you have a system that allows you to have everything centralized, you are already kind of there. And then if you have a system that allows you to integrate different hardware from different volumes, then you have a way smoother transition between an R&D phase and a production phase, and also allows you to be faster, and so to be faster to your money, basically. So this was the general overview. Now, I would like to enter now this more interactive part. What are we going to do is the following. I'm going to show you basically our control system that doesn't contain yet all the features I mentioned, many of them, but not all. We are still working on it. And I'm going to switch very soon to our web application. But first, we are going to program, or we are going to take a look at a process together. And in order to understand this, I need to make you understand like what would be the hardware we are trying to control. What is the machine that we are going to try to control with the control system? And I simplified it as much as I could so that it doesn't become too technical. The idea is very simple. You have just a vessel where the cells are, and then you can just pump some medium in, take some medium out, circulate some medium here, and then you have a bunch of sensor, temperature and pH to just check if the bioprocess is running correctly. Okay, so very simple. Medium in, medium out, circulating. Yeah, and then you have a pump to take out the cells. When your cells grow, you want to take them out, you have an harvesting pump here. That's all you need to know. And now I'm trying to share the other screen here. Let's see if it works. So now you should be able to see the web application I was talking about. So this is where you land when you log in. And here you see we have 3 bioreactors nicely running. And to show you a bit how does it work, I will use this test bioreactor. So I'm gonna click now on the bioreactor so that you see what is gonna happen. So here I was talking about this having a centralized place. So here you see that you have all processes that have been around with that machine are here, nicely saved. You can even say, oh, this is a favorite one, it appears at first, stuff like that. Everything is saved here. And now I'm trying to show how this easy programming works. And for that, I'm gonna open this process that I already prepared for you because developing a word process with you, it would have been taking way more than 20 minutes. So you see here on the right here, there is a process tree and you see different phases here, right? So we program here a first phase where we say, okay, we have a machine. What is the first thing that you need to do? Well, you need to put some medium in the machine, or in our case, we need to fill the tubings. So we call these steps fill tubing, pretty obvious. And then what we did is that here you remember the pumps I was showing you before. Well, you want to pump some medium into the system. So you see, you set here the speed of your pump. You say, I want to pump some medium in. You put the speed, and that's it. And here, since we are not really sure, we are a bit R&D phase, so we really don't know when the tubings are refilled with medium. So we said this is a manual phase. We are going to say manually to the system when we are going to go to the next phase. Obviously, you can also set a duration, so you want this for 2 hours, but we don't know how much it's going to take, like, so we say it's manual. Then what we want to do is that we want that the bioreactor is at the right temperature. So we set the different heating element at 37 degrees so that our cells are happy. And we know that it takes a few, sometimes to equilibrate with the temperature and also with the pH here, pH controller, we set at 7.4. It's gonna take some time. So we said, okay, we are gonna give the bioreactor 2 hours to really equilibrate at the right parameter. And then we decide, okay, then we are ready to add some cells, right? And here again is a manual phase because this is an operation that in R&D phase is still manual. You want to add the cells manually to the system. And then the fun part starts. After you have added your cells, here you see you have a group of 4 phases. And these 4 phases are, we perfuse the cells with medium all the time. Then the cells grow and we harvest them. And then we remove some old medium from the system and we add some new medium. These 4 phases here, all of them, the sum of the time, they take 1 day. And we want to cultivate the cells. So we want to run these 4 phases in a loop for 14 days. So we repeat this thing for 14 days. If, for instance, you would like to have 3 weeks, you just put 21 here, and everything would be okay. And here, just to make an example, the harvest phase, what does it mean? It means, for instance, that here you have the medium, the harvesting pump at a certain speed. It means that the pump is going to run and take your cells out. And we know that this is going to take 5 minutes to get some cells out. And after these 5 minutes, automatically we go and this taking some medium out and adding some medium in. this is pretty much the basics of how, in our case, how it works. You see, we have these for loops. We are still working on these if conditions. I'm not able to show them yet, hopefully very soon. Yeah, so I think maybe it's a good point to answer a few questions here.